Okay, good morning, all of you. Today, let us continue with the topic that was the real numbers. Okay, in the previous class, we were discussing about the classification of the numbers. In the previous class, we discussed what are the real numbers, what are the prime numbers, what are the composite numbers, what are the co-prime numbers. Then we discussed about the twin prime numbers. Now, further in this chapter, let us move forward. Our today's topic is that is divisibility. Our today's topic is divisibility. Okay, now indivisibility means when we are going to divide a number by another number. Okay, so let's write down a non-zero integer. A non-zero integer is said to be a non-zero integer is said to be divide an integer b is said to be divide an integer b if there exists if there exists if there exists an integer c if there exists an integer c such that b is equals to ac such that b is equals to ac. For example, uh, 7 divides 6. For example, 7 divides 42. 7 divides 42 because there is an integer because there is because there is an integer 6 such that 7 into 6 is equals to 42 such that 7 into 6 is equals to 42. Okay, it means if a non-zero integer a divides an integer b, then it can be written as if a divides b. If a divides b, then it can be written as a straight line, then b. The meaning of this is a divides b. Okay, or it is read as, and a if a does not divide b, then it is if b is not divisible by a. If b is not divisible by a, if b is not divisible by a, then we can write it like this: a will cut this line. Okay, that is the notation when b is not divisible by a. So that's all about the divisibility. Now let us come to our next topic, or the very important topic from where our chapter starts, that is Euclid's division lemma. So that is Euclid's division lemma. Euclid's division lemma. Uh, Euclid was a mathematician uh, who is known for its uh, geometry elements. He has done a lot of work in geometry, and Euclid's geometry we already studied in our previous classes. But he has some importance in number theory also. He has done some work in number theory also. That's why, and he has given Euclid's division lemma. Now, before starting the statement of the Euclid's division lemma, let us describe the meaning of the term. What is the meaning of the lemma? So first, just define the term, that is lemma. Lemma means these all are the proven statements which does not require any proof. Okay, so here we can write these are the here we can write these are proven statements. These are proven statements. These are the proven statements which do not require any proof. Which do not require any proof. Okay, these are the proven statements which do not require any proof. They are taken as the granted. Okay, now let us come to the statement of the Euclid's division lemma. So we come to our next, that is the statement. Now, what is the statement of the Euclids division lemma? Let a and b be any two positive integers. Let small a and small b, let small and small b be any two integers, be any two integers, be any two integers, then there exist then there exist there exist unique integers, then there exist unique integers, q and r, then there exist unique integers q and r such that a is equals to bq plus r, such that a is equals to bq plus r. Okay, where r is equals to where the range of r we can write here, where r lies between, where r is greater than equals to 0 and less than equals to b. That is the range of the r. Okay, here we can write if b divides a, if b divides a, then in that case the number is completely divisible, so r is equals to 0. Oh, so that is the statement of the Euclids division lemma. Okay, if a and b be any two positive integers and there exist unique integers q and r such that a is equals to bq plus r. If b divides a, then r is equals to 0. In that case, remainder will be equals to 0. Now let us solve some problems based on the Euclids division lemma. Okay, so write down our first question. Okay, show that any positive or integer, show that any positive or integer is of the form 6q plus 1, comma 6q plus 3, or 6q plus 5, or 6q plus 5, or where q is some integer, where q is some integer, where q is some integer. Now, how to solve this question? Let us come to the solution of this question. Okay, here we are given that let a be any positive integer. Let a be any positive integer. Let a be any positive integer, and b is equals to 6. And b is equals to 6. Then by Euclids division lemma, then by Euclids division lemma, where exist then by Euclids division lemma, there exists integers q and r, such that integers q and r such that a is equals to 6q plus r. Okay, here we have taken the value b is equals to 6, where r lies between. Here we can write where r is equals to 0, 1, 2, 3, 4 and 5, since r lies between 0 and 6. Now if we take the some cases, okay, we take the first case here. For the first case, if r is equals to 0, if r is equals to 0, then a is equals to 6 cube. Okay, then but we have to show that every odd positive integer, but it is a multiple of 2, so it is not odd integer, not a odd positive integer. It's not odd positive integer. Okay, in the second case, if we take the value of r is equals to 1, if r is equals to 1, then a is equals to 6 cube plus 1. Now it is of the form 6 cube plus 1. That's why it is an odd integer. So it is a odd integer. It is an odd integer. Okay. Similarly, we can take the another cases. If we take the r is equals to 2, then again, if r is equals to 2, then a is equals to 6 cube plus 2, which is not an odd integer. It is a even integer because it is multiple of 2. Now in the third case, in the fourth case also, if r is equals to 3, then again a is equals to 6 cube plus 3. Okay, it is again an odd integer because it is a multiple. Okay, or finally, if we take the for r is equals to 4, it will not be odd integer. We can directly take r is equals to 5. If we take the value of r is equals to 5, then value of a comes out to be 6 cube plus 5. Okay, it is also odd integer and it is also odd integer. That's why we can prove that any odd integer is of the form 6 cube plus 1, 6 cube plus 3 or 6 cube plus 5. Okay, so by this way we can solve the questions which are based on the Euclids division lemma. Okay, we will solve the few more questions in our later on classes. Okay, that's for today. Thanks.